Hi, everybody. I'm Matt Souder, and today I'll be presenting my autonomous robot with a 3 degree of freedom manipulator. So, to introduce my robot, here it is on the right. So, it's a four-wheeled robot with the manipulator on top, and it's going to follow a black line using infrared sensors, and it's also going to use an ultrasonic sensor to sense if there's any objects in its path. If there are objects in its path, it's going to use the arm to move the objects out of its way. Here's a further breakdown of the components of the robot. So I'm using an Arduino Uno with a DC motor drive shield. And that drive shield is going to power the 4 DC motors. Also using a servo motor driver to control the 4 servos within the robotic arm. 2 infrared sensors, and those are at the front here. So that's used for the line following. And then the ultrasonic sensor, which is detecting any objects in its path. And a 7.4 volt lithium battery. So here's a wiring diagram to further show how I've related everything in my circuit. So for the forward kinematics, I built this diagram on the right to build a DH table. In my DH table, you can see the link lengths, D1, D2, and A3. So I use this DH table to build the transformation equations for this robotic arm. So here are the four equations for the 4 orders here on the DH table, but then I've used those to build TO1, TO2, TO3, TO4, and then use those as well as the Z and the O vectors to solve the Jacobian matrix. So I did that by hand. Then I also used this code in MATLAB to find the Jacobian, and the two of them matched up. So here's my final Jacobian matrix. Has the link lengths in it in millimeters. So for the inverse kinematics, I did a top view and a side view. So for the top view, it's in the XY plane. So I'm able to find theta 1 is the inverse tan of y over x. For the side view, I'm looking for theta 2, theta 3. So I'm solving for that top triangle there. So we can see the right side of the triangle is equal to the z position minus the length of d1. And then the x length of that triangle is just that x coordinate. So using the two of those, we're able to find the value of r, and then use that value of r to find theta 3. For theta 2, we're looking for these angles alpha and beta. Alpha, you can kind of see there in the red, it's the full angle to the left of that triangle. Beta is the top portion of that triangle, and theta 2 is the lower portion. So I found the value for alpha, value for beta, and then theta 2 is equal to alpha minus beta. Next, I simulated the arm in MATLAB. Excuse me. So the bottom portion there is how I define the arm. All the link lengths, where the joints are positioned, my initial position of the robotic arm. And then I feed that into an equation to find the forward kinematics and display that using X, Y, and Z coordinates of the end effector. So grabbing object, that's my angles that I want the robotic arm to move. Feed that into the robotic arm I built. Convert it using this equation of forward kinematics, which uses a rigid body tree and then a transformation to a coordinate system so we can see it visually. So here is the simulation for my robotic arm. So that's the same position that's the arm starts in, as you can see here. So there's the x-axis, the y-axis, and the z-axis. So this has the end effector in the negative x direction. Then the big red circle, that's the car, that's the base. Link 1, link 2, link 3, and the end effector. I also have each of the revolute joints defined. So that's the shoulder joint right at the base of the car. Then there's the elbow joint and the wrist joint, which is at the top. And then the end effector, that's just going to open and close it. So define that too. So I'll put this into a 4 view and start the simulation. So it goes down, it grabs the object, moves it out of the way, and then resets back to its neutral position. And this is exactly how the arm is going to behave in the robot when you see later in the presentation. So from this, I can get the coordinates of the end effector when it's going out to grab the object and move it. And it's presented here in the graph. So the yellow is the x position, blue is the Y position, and red is the Z position. For the Arduino code, I started by setting up the pins and setting the initial servo angles. And then there's a code for the obstacle. So I set the trigger for the ultrasonic sensor and then defined the distance. I wanted it to be in centimeters. And then I emitted a distance under 2 centimeters to just emit any triggers within that range. So this is the main loop for the robot. So it's going to sense if there's an obstacle, and if there is, and it's under 11 centimeters away, it's going to trigger. It's going to stop the wheels, trigger the arm, and then it'll go back to, okay, obstacle's gone. I'll continue to follow the line. So here's the line following aspect of the code. So with the 2 infrared sensors, they're either 0 or 1, and depending on if they're triggered by reflection of the white surface or not, that's how we get the 0, 1. And so I get 4 different cases. 1, 1, the car's going to stop. It's just the black surface, not going to go forward. 0, 0, the car's going to move forward. And then so if the left sensor notices the black line, it's going to turn the car left to reposition itself to follow the line, and the same for the right. And then here's the code for the robotic arm, just setting all the servos and changing its angles as I want it to grab and move the object. So here's my simulation. So it's following the line, notices the object, moves it out the way, resets the arm. You can see the infrared sensors triggering, the green ones in the front to follow the line. And it's the second object. Moves it and continues. So some challenges I ran into when creating this robot, it was overshooting turns. So I had to introduce a delay for the infrared sensors so that it wouldn't just take hard turns. It'll stop and reassess the situation. The ultrasonic sensor had some noise. That's why I made that initial 2 centimeters in the code to emit any distances in that. Because when I would start the robot, it would automatically trigger the arm. And the servos are finicky. I'd like to upgrade them to some better servos. That way it'd be a cleaner transition when moving the objects. But so that's the summary of my project. I used applied kinematics for the manipulator to move objects out of its path. And I achieved an autonomous robot using different sensors and devices. And in the future, I can upgrade some of the parts to make it a little more seamless. If anyone has any questions, feel free to email me. My email is on the screen here. I'd be happy to take any questions. But thank you for listening to my project, and I hope everyone has a great day. Thank you.